guy by the name of Mike Grawl, and so normally when he puts it out in the Geophysical Society of Houston, it's so outrageous. So I clip out all the craziness and capture the essence of it. Some of the craziness is still there, and it's part of Mike's sense of humor. But it is particularly good for a class like this, dealing with information theory, reflection, refraction, the whole seismic methodology. It's a totally different perspective. No one would ever accept it as a manuscript in a book because it's so completely crazy. But it's a lot of fun, and Mike is a master teacher for the SEG. So when we talk about deconvolution using inverse filters, the D-transform, he's also fond of doing that. That's quite a bit of it. And I think there's like 70 PowerPoint pages that I captured that takes you from, you don't know anything about geophysics to some rather sophisticated deconvolution. So it's a nice, I know now you're up to about 5 or 6 texts out there, pick and choose, but the Nuggets is an easy read. It's almost a cartoon, but it's really neat. The mid-semester exam I'll hand out today at the end of class. It's due in my mailbox next Tuesday at 2 o'clock. I've decided to change the syllabus. Instead of one final exam, 2 exams. I want to give people plenty of time, and so this is going to be one of those things where it's kind of extrapolative thinking. One of the questions is pretty easy. One of the questions takes some time, and that's it. So that's the day, do it a week. Other questions before we get started?
Yeah, about the 2 exams, is it going to be the 2 exams, the final?
Yeah,
the last one and
the total is still 50% of your course grade. Okay. So what I'll do is simply fix it to where the 2 exams become 50% of your course grade. Right? Nothing's changed in that. It's just that instead of giving you one rather big exam at the end, I thought I would make the exam smaller on the final and allow plenty of time to take it. It's going to be a 6-time exam on the book at 6 times.
What's the final exam? Take home or
take home? Take home, open book, open anything but another person. But it'll be one of those deals where you open a bag at a certain hour and you have 5 clock hours to take it or whatever I say, and you just put it back in the bag and yeah. But I just wanted to shorten by doing some other early. Yeah. Question? That was a good question. Final project is the lab is 50% of the grade. The final project is 40% of is 40% of final grade. So that will begin to take shape on about week 10. When we stop doing collaborative processing and we do all by ourselves. But we're not there yet. We've got about 2 more labs, 2 more lectures, and then I'll be talking about some specific items within the field of reflection seismology, like AVO and shear waves, and haven't got anything to do with your final project. It will not distract you from knowledge necessary to do the final project, but it will complete your education on those things that I think are still germane to the business today. So, whether you do AVO using just P waves and worry about qualitative and quantitative AVO with P waves, or whether you evoke the power of the second body wave, I want you to be aware of that. That's it. Okay. So in review, the last time we talked about 2 things. One, very quickly, and that's statics. I just want to make sure you understand that statics is really a rigid shift of a trace. It doesn't dynamically change anything. It just moves the trace up and down. Think of it as if you had the mosaic, the picture, and you dropped the sucker and it was glass. Oh my God. And you tried to reconstruct it. And that's what happens. The near surface does a really crummy job of distorting the various traces that you're going to comprise a final stack trace after you make all the dynamic corrections. And static collectively tries to rigidly reconstruct it before you drop that glass. That's the picture I would invoke. So if this is the before of a static reconstruction and this is the after, this is of course a 3D data time slice, if you will. And before you can barely tell where features are, and after you've done the static, whether they're elevation or refraction statics or residual statics by adjusting the normal move out, adjusted data, whatever it is, you finally reconstruct it to what it looked like before the near surface ruined the picture. But it's a rigid adjustment. It's moving the trace intact. There is no adjustment except the so therefore the word static as opposed to dynamic. Dynamic as in NMO correction. We spent the better part of the time though talking about filtering, and we want to make sure everybody was familiar with the integral transform over the full line. That is to say, from minus infinity to infinity. The kernel for the integral transform of the Fourier variety looks like this. And so if you put in a time function g of t, what you get out of this is a capital G of f, because the kernel has both time and frequency within it. And it's used so much, that particular integral transform is used so much that I bring it up again. And one of the things we used last week in talking about designing a filter was the fact that convolution in the time domain is multiplication in the frequency domain. So if you're using data in the Fourier domain, and you have an amplitude spectrum and a phase spectrum, and you're trying to do it in a filtering sense, if you take a filter that is designed to pass frequencies from A to B, then what you do is design a filter that has an amplitude spectrum that goes from A to B. And the phase spectrum is 0. You don't want to mess with the phase that's there, and you multiply the amplitude spectrum. And so every place you have a 0, what was in the data is removed by it's been zeroed out. That's how a filter works in the frequency domain. And again, in the FK domain, that particular, if you then not only transform the time part of the sinusoid, but the space part in the FK space, this is a particularly useful item. And what I want to make sure you understand is, in the landmark data set example, the reason that this is very useful for data like that, all of that data is simply ringing in the water column. You're getting picture 1, 2, 3, 4, 5. And the only travel by that wave is in water. So if you do a constant velocity stack, a CVS, and you have just water velocity in there, so the entire set of traces has a CVS of just water velocity, then what will happen is you'll turn your primary events inside out if you use that NMO correction. All of your multiples are going to be flat. So in FK space, they reside here, and they can be easily removed by zeroing this part of the FK space. Then you do, if you simply take this picture again, rescale it, the items that you're interested in now scale up like this. If you do an inverse FFT of both time and spatial parts of that waveform, you'll end up with this picture again. Now the primary is the only thing left, but it's turned inside out. So you have to do the NMO correction in reverse to turn it into then a primary less the multiple. And if your signal is bouncing around that water column, you can very effectively do this to the exclusion of adding any other artifacts in the process. Very useful thing to do. Then deconvolution, the text here reads for itself. We're trying to design, to get rid of those things that are undesirable. The Earth response, such as reverberation, attenuation, ghosting. And in the lab, we did predictive deconvolution. that had a normalization of least squares, so an L2 predicted deconvolution. And what we talked about in lecture was if the prediction distance as a unit, and so it no longer is looking for getting rid of reverberation, all this is going to do is broaden the waveform. Okay? It's going to take the wavelength and compress it to a Dirac delta function. Try to do that. That's the desired output of your wavelength. And in doing so, broaden the spectrum such that in the convolutional model sense, you have a broader spectrum. That's what spiking decon tries to do. And just mention that in spiking decon, there's two versions of it. There's the deterministic spiking decon, and there's the stochastic or statistical spiking decon. Okay, deterministic says, I know what the wavelet is. Most times you don't. Statistical says, I don't know what the wavelet is. I'm going to use some magical process that'll get around that, and that's what we talked about later. We use a particular mathematical invention called the Z-transform, and so for the discrete Fourier interval, we replaced everything but the k in that discrete Fourier interval part, and so that became z. And so by substituting into that previous equation, we got this thing called the Z-transform. And it is a polynomial of the z variable, where the power of z represents the time delay of the discrete samples in the time series XT. If that's the case, we showed that it was Fourier-like. You could do multiplication of that Z-transform, and it was just like convolution in the time domain. And then we used it to define inverse filters. So we found that we could take a wavelet that was in the Z domain and simply do long division of that polynomial. And so if you had a WFT, a wavelet that looked like this, that was front-loaded, that is to say minimum phase, something like that as opposed to a whoosh, okay? When you do that, this minimum phase wavelet in the Z domain becomes simply 1 times z to the 0, which is just 1. And the second term would be minus 1/2 times z to the first. Okay? And so forth. So in that case, we just had a two-tuple, so we have just two terms in there. And all you have to do is take the inverse of that, so 1 divided by that polynomial in the Z domain that was representing the Z transform of the wavelet. You got another polynomial out of it, and one of the things to notice was that this particular polynomial was in fact converging. So the more terms I had, the better it gets. In this case, we stopped at 3 terms. And so in the Z domain, the answer was 1 plus 1/2 z plus 1/4 z squared, so forth. In the time domain, you simply replace the SIGN, pluses and minuses, with a comma, and the 3 tuple that would come out of that would be a 1/2 and 1/4. That's the filter that would purport to undo the wavelet and turn it into a spike. Okay? So then when we just demonstrate that, we just put in convolution, and we take our original wavelet here, and we convolve that with this design filter, and then do the arithmetic, and out comes this result as compared to the Dirac delta function, if you like. It's pretty darn good. It doesn't work when the wavelet is maximum phase, because when you try to do this 1 over that maximum phase wavelet to determine the filter, what you get is a polynomial that is not converging, but it's diverging. Every term gets bigger. So if you say, I'll pick a 4 or 5 term, it doesn't get better, it gets worse. And if you plug that in and try to take your maximum phase wavelet and compress it to a spike, you get this right here, which is horrendous, because the 4th term in that vector is the biggest term there. That's not cool. That's not cool. And then finally, we talked about Wiener filtering. If you want to read a lot about Wiener filtering, among the references would be Mike Grawl's Nuggets, or for that matter, Ozzy Omar. And in the sense of that, you simply do an autocorrelation of the input wavelength, and that occupies the inversion matrix here. And this over here is doing the cross correlation of the input with the desired, and then the equation says these are the terms of the inverse filter that emerge. But I just said the magic word. You got to know what the wavelength is. You got to do the autocorrelation of the wavelength. If you don't, if you know that, that's called right there deterministic spiking decon. If you don't know what the wavelength is, which is 90% of the time, you don't have any idea, then what you found out was that instead of autocorrelating the wavelength, I autocorrelate the trait. And the trait was defined as the reflectivity sequence involved with the wavelength and all of its warp, all the noise and distortion was combined into one item there. So if you cross-correlate that with itself, both left and right side of that equation, what you found was you could change cross-correlation to convolution by just changing the SIGN of these two terms of that. That's from the very first notice that correlation and convolution was just alike, except one had the vector rotated before moving. So it's that notation there. Once you get to this stage, you have convolution, 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 and that's commutable. So they can be in any order. That being the case, you put this one down here, and you put this one over here, and you rewrite it, and now change for each of these terms, convolution to correlation, lets me take away the negative sign that was there. Convolution to correlation, the negative sign goes away. And you said, well, so now what? Who cares? What's that going to do for me? And the answer is, hey, if this right here, if R of T, the reflectivity sequence, is random, and it's not, I mean, a random number is a very special mathematical construction. But if it approaches being random, if that's the case, then the cross-correlation of R of T with itself is the Dirac delta function, and so it simply mimics this guy here. Or put another way, the autocorrelation of the trace is the same as the autocorrelation of the wavelength if the reflectivity sequence is random. That's the whole basis of spiking decon for the majority of it. So if you push spiking decon in Promax, it'll do that. It'll take some part of the whole trace of your designation and do an autocorrelation and begin to undo trying to find what an inverse filter is for that. Yeah?
What is CFT?
C was, I don't have that page up, that was the page before showed that C was the wavelength involved with all of the junk, including all the distortion in it. So it was, originally it was WFT, and then there was another term, and they got combined into CFT, which was basically, when all the smoke cleared, the wavelength and all of its distortion. So a wavelength with all the warp. So just a combining of that to let me separate it from the reflectivity. So in that case, you go look at all the details. The spiking decon out of Promax, if it's deterministic, it says it's a flat layered earth, there's no converted waves, the wavelength is stationary. I mean, that's saying that the wavelength is moving through the earth and it's not changing with time. And that's not happening. I mean, it's changing, but we have to assume that it doesn't. And then bigger, the real wrapper is noise is zero. This is why we do spiking decon to stack traces, which is my next, or not very far away in the next set of slides. You know, until you have stacked traces, you don't have, you're not anywhere near having signal to noise ratio such to accept that. Or put another way, if you do spiking decon on land data that haven't been the power of redundancy hasn't been fixed with stacking, it will ruin your data. And the best way to do it is do some process and try it before and after. You can't even, your after will be just a complete noise. It will destroy your data. And a lot of people say, well, I can simply, I can front load, I can take this inversion matrix and do a diagonal loading, so-called pre-whitening of the data. You'll have to do so much pre-whitening it becomes the identity matrix, and it recreates the trace. It doesn't do any filtering at all. So you can't do anything about it unless your noise is kicked down with stacking. This is a waste of time. Do not do spike and decon until you've got your best signal to noise ratio. Then do it. Predictive decon is another animal for different reasons. And deterministic is you know what the wavelet is. The statistical or stochastic decon, the standard button to push and throw back, same thing all the way down to here, but you don't know what the wavelet is. All you have to assume is RC is random. Sometimes it looks pretty random. And the wavelet is minimum phase. Okay. The example I showed, this is some work in China at a poster session of the SEG. That's the before, here's the after, an enormous improvement in the bandwidth of that signal. The only other thing I showed that day was just kind of a wacko thing, but in 1981, I think it was, when Bert Valley was putting together his book known as The Seismic Expression of Structural Style, a friend and I, Mike Howard, and I put together this page 25 of his atlas. This is after he heard about what we did, and I'll leave it here. It's in the second floor library for your, but just to show what we did, I was processing data in the mountain front of western Oklahoma. It was a very poor data set. I felt like I was creating things in the section because I was taking a lot of liberties with the processing package that we had to process. So Mike says, well, why don't we replace your field files with random data and see what happens? So we did. We just took the standard field files and replaced it with data like this. This is the kind of files that we ended up with. The brute stack here, this is the brute stack. It looks pretty crummy, but if you look at the final stack, after I was doing a lot of nonlinear processes, this is what you got, some random data. It's just a precautionary. And Bert Valley wanted to show his audience that if you're going to do structural processing of very complex features, you got to realize that you can create spots on the tape. Okay? And you do this when you go into nonlinear processing, such as adaptive filtering. If you look up, you type in adaptive filter and hit a button, you'll get an adaptive filtering package. And hit the little red button, and it should tell you that it's a nonlinear process, where instead of modifying an amplitude spectrum, you're actually replacing stuff like that. So you can create things that are not real with process. Just be aware of that, because this is a good example of how it can be done. Okay, so that was last week, or 2 weeks ago. Okay, so this week we want to talk about velocity analysis. It's not nearly as long a lecture because you've done a velocity analysis already in the laboratory, both constant velocity stacks, the velocity spectrum. I'm going to review parts of it. Excuse me. Also introduce you to the Dix interval velocities and do some other things. But let's start off by asking the question, what is this? I think we've already talked about it. But most of this course, and it will switch in about 2 weeks, most of the course is what is this, and I mean what processing steps got you to this point. And a lot of times I can ask the other question, what is this, as an interpretive question. So from about the last 4 weeks in the lectures, it's becoming more of an interpretive kind of a class. because you guys are working on your project, and you don't need me to add another tool that you might have used, so I'm not going to do that to you. I'm just going to show you things that are more interpretive and yeah. So if I was to ask, what is this on the processing part, you would say, well, that's a common offset gather. And it is. This is landmark data, common offset gather. Here's the water bottom. This is the water bottom. If you have one trace for every shot, that's what you'll get. The Q of seed water is 65,000. You get huge fidelity on seismic systems and water. So you get really nice pictures. But you notice I've cut this off at 700 milliseconds. And that's because anything below there, you start to get a re-imprinting of this with that nasty reverberation, the multiple. The other question is, okay, so what, in that sense, what's this stuff up here? Remember, the reflection event's up. So here's zero times, and here's the very first reflection of the water bottom. Remember now, in reflection seismology, that the reflection event is never the first event. So what's the first event up there? Direct wave. You know, it's a different looking at it, but that's the direct wave coming in just the same all the time. And if you want to see how consistent the shots are on the air gun, one of the ways is to look at this and say, how clean are my shots? And you spread that out a little bit and look at the, and blow it up bigger. You know, how regular are the shots? The best way to see it is look at the direct phase on any marine section. And then play back the very first part of it, and you'll see what the geology looks like. Don't do this with land data, it's a waste of time. Marine data, look at the short trace, do a common offset gather, and then look at it for consistency of the downgoing source. That might confuse the issue. One good way to throw out sources is to say, wow, the shot number 12 is terrible. It was, you know, obviously something blew up or something, you know, you throw it out. If you're trying to do amplitude processing, if you're trying to do structural processing, who cares? But the other question is, what is this? Of course, geologically, that's a reef. This is a flooded reef. Here's the reef here. Here's the lagoon back here. Here's the four reef facies looking like this. Okay? So, now here's the deal. What you do when you do that, you put that up on your wall and you say, okay, do no harm. Now you're fixing to process all the data. You want to make sure you beat that section, not ruin it. Okay? So from there down, you're going to have to build signal to noise with the power stack. But from there up, you don't want to ruin that section. You don't want the stacking process to look worse than the 100%. So if it does, you need to go back and reevaluate the processing you've done and say, well, what did I do to cause that? The final product looks a lot worse than my simple product. Always a good idea. In fact, it's always a good idea to look at the data. Don't be so distracted with the abstraction of the velocity spectrum that you don't go back and look at the data before and after. Did I make this better or worse? And better or worse means that it fit my working hypothesis. It's just a scientific method, that's all. And it gets a little artsy, but you got to have an idea of what it should look like when you move from there. Okay, typical flow for 2D and 3D velocity analysis. This is not new to you. This is new to you, and I want to just illustrate this. So here's this equation. The only equation we need to know, Tx squared equals C0 squared plus x squared over v squared, where v is the normal move out of the reflection method. Now what if I plot not time, but time squared against x squared? Okay? Then this equation can become thought of as a straight line with a slope and an intercept. Now, mind you, where did I get these data? These data could be a common shot point gather, a common midpoint gather, looking like this, And that's a reflection event with a point A and a point B. And each of these points, A and B, have a time, and they have an offset. Here's the offset for that field file, or common midpoint gather. Now I said field file. This could be a field file. It doesn't have to be a common midpoint gather. You've got reflection events that satisfy that equation. If it's a field file, then instead of a point down here, it kind of spreads out a little bit. In this case, you average the information, but no big deal, really. You can process, assuming that they're common midpoint gathers, they don't have to be for some things. So if you plot A and B, not T and X, but T squared ordinate against X squared abscissa, and you get these points here, A and B, and if you just have 2 points, you can draw a line, but it's pretty terrible because you'd like to have more degrees of freedom. But you can draw a line, and you'll intercept at this point here, and that's going to be T0 squared. So if you're trying to form a velocity function, what you need to have is a time and a velocity associated with that reflection event. And this time would be the square root of that, and the velocity would be the square root of the inverse of the slope of that. Okay? So guess what? You can take a common midpoint gather of traces on your desktop, or it can even be a field file, and all you're doing is averaging, and you can make a velocity analysis. Just like that. T squared X squared plot. Handy. If you want to look at, you don't have a computer handy, you can do a T squared X squared plot and derive the beginning of the velocity function. More on this in a minute. By the way, this is Eichel and Amundsen. Here he's doing it on a big scale. That's probably a common midpoint gather, all the points shown. So there's quite a bit of jitter. But when you do that, that's what you'll get, and you'll get a very nicely defined line. Here's T0 squared, and the slope of that is 1 over VRMS squared. Because we live on a layered Earth, and VRMS is the applicable adjectival for velocity for that world, right? It's the move-out velocity for a reflection event in a multi-layered Earth. So that's Eichel and Amundsen doing, not for points A and B, but for all the points of that. The only thing I would caution you is don't go too far out. That is to say, if you go too far out beyond, say, X equal to Z, Z being the depth of that reflection, then that curve is no longer a straight line, it begins to top over. Because the equation doesn't work for at the bottom. Okay? So this is applicable for X about the same as Z. You can do that. Okay, let's go back to stacking. Here is a common midpoint gather having 500 traces. Now, Eichel and Amundsen is only showing 10 of these. But you can see the reflection event because you know it's there. But the signal-to-noise ratio of this is about 1 to 1, maybe 2 to 1, between the noise and the signal. And so if that was the signal you were trying to do a spiking decon with, you're in trouble because you got noise that's not zero. In fact, it's empty-handed with the signal. So if you wanted to try to do spiking decon to improve the convolutional model sense of wavelength compression, you can't do it with those data. But if you stack these data, here's the stack of that. And these are real data, and that's a real stack. Now, it looks incredible because, once you add it all up and then divide by the number of terms, the noise goes to something that doesn't even show up on your plot. But if you deconvolve this kind of a wavelength in that sense, yeah, you're in good shape. There is nothing more robust than normal move out in stack. And so those of you, I know Ola in the other class, when Peter Ike was talking about common numbers of stack and even 3D, it was in the thousands. People have gone to having a redundancy of several thousand on 2D, and not uncommon to have 1,000 on 3D. in a bin. And that's a new thing. I've never had stacks more than about what you have in lab, 30 or 40, something like that. But they're finding that done right, the power of NMO and stack is so big that they do it at that level. Again, square root of the number of turns in the stack is the basic improvement on signal to noise for Gaussian noise and so forth. Now you've seen constant velocity stacks in the lab. I want to make sure we understand that the reflection event with no move out corrected looks like this. If you do it exactly right, it looks like this. If your velocity is way too slow, it'll turn it inside out. And if the velocity is too fast, it'll leave it uncorrected instead, or partially corrected. So if I go to a constant velocity stack panel, that's the first thing I'm going to do with land data. If I've got land data, I don't look at a spectrum until I'm way down the road, because it's so, the data can be so noisy that you really want to look at a constant velocity stack panel. You want to pick 6 or 8 or 10 common midpoints in the middle of your, where you've got full stack in that, and you want to play those out to where you're doing this kind of a thing to a collection of traces side by side, and so doing, creating a little piece of geology that's either in focus or not. Even though it only has one velocity, there's kind of an art form for picking these things. And let's switch to, let me switch to this one to do it. Let's look at the landmark data. And you say, okay, I've got an event here at about 1,000 milliseconds. It looks pretty good for a velocity of 1612 meters per second. But that's with panels chosen that are 3 times the original slowest velocity. What if I reduce that to 2 times? So before you would have said, okay, 1612, but now that same event looks a lot better for about 1643 meters per second. Yeah, just opened up the aperture of your investigation. And if I go to 1.5 times, that same event at 1,000 now looks pretty good, maybe at this choice of 1677 meters per second. So what you're doing is you're refining your choice. Your T0 stays 1,000. Your velocity, moves depending upon what sort of, and here it is 1.25, and now here's the same event at 1,000, and now you say, I think probably this one looks really good. So maybe 1665 meters per second. Now after a while you have a law of diminishing returns. What you're trying to do there is, because they're quick to run, is you're trying to get a quick and a crude velocity function to maybe do a one-dimensional stack of your data before you do spectra, because that's going to be the guide bars on your spectrum. It's going to be about that. So if you can make several picks to get you a basic velocity function based on what you see on the constant velocity stack, that becomes the guide on a spectrum that you don't stray outside of it. Make sense? I like CVSs. To me, they're a real quick way to get a grip on what's a good velocity function, to give me a rough idea of to do a brute stack, and then I can see, okay, I've got these particular problems. I've got to spend a lot of time with this or a lot of time with that. And let me get down the road with a quick stack, and I call that a brute stack, meaning the boss wants it in 30 minutes. Okay, great. And you do something real fast, and you throw it out there. If your data are real good, you can't almost do anything wrong. If your data are lousy, you can spend weeks and months working on data, and you just can't, it just collapses over. A lot of times, something that's real weak data, like this is the Savannah data, this reflection event right here is real at these velocities, but the best way to do this before you get rid of all the low frequency crud And that way, your velocities on Savannah on a constant velocity stack are short like this. So every problem is different. So. Just a pictorial form. If all of your velocities are right, this is your final common midpoint gather that you will stack together. There's a reflection there. There's a reflection here. There's a little reflection right there. Okay. Now, if your reflection event that was here is 800 feet per second too slow, then that same event is going to look like this. Okay? If in fact it's 800 milliseconds, 800 feet per second too fast, that same event will look like that. Okay? This just shows you the panels either side of that. Here's the other thing. Here's the same common midpoint gather. This time on the left, no muting whatsoever. Okay? So what you realize is that I've got a nice reflection event here, but it gets really ugly on the end, and that mute is going to come in and cut it off. It's just another reminder that if your objective started at about 0.8 seconds, you got a problem. Because you've got a survey that is designed where you'll have really crummy stack levels at the shallow part of your interest zone. So you didn't have enough. You had too big of a delta X on your survey, and there's nothing you can do about it. Okay? Every survey has a focus. What am I looking at? Now for sure, you can see that and also see the bigger picture. But when you start to get a shallower than your focus, these kind of things, that you just stuck with it. You can't do anything about it. And that's just a current leading edge article on these kinds of issues that I read in your, just as an example, to read a current literature on this. Similarly, this is March 2009, showing a common midpoint gather after processing and before processing. And I'm sure what's happening here is mainly residual static and all kinds of signal improvements. So you've gotten some major improvements on the kind of authenticity between the before and after on the reflection event. Here's the catch. You're going to take all these and sum them into one trace, and you're going to put that trace next to a whole bunch of others. You'd be amazed if you took the left side and did that, and the right side and did that, and put it the two sections out there. They're hard to tell apart. Because stacking does so much of the work for you that when I think I've got to work like crazy to get something like on the right, if I just take the left and use this and then compare the final section, I can do the difference. And when you can't, then you tell me two things: the power stack, and I need to have as much stack as possible because of its power. And I can do other things to improve signals like that, like really do a deconvolution. And if I know what the wavelength is, I can get really saucy with it. Yeah, just some comments like that. Okay, the normal move-out equation works fine when X and Z are about the same. When they are not, you have to put in long offset corrections, that is to say, another term in the move-out equation. Not the third power, but the fourth power of X, because you skip the third power because of symmetry, just like you did the first power. And there's also issues with anisotropy that begin to come up. That is to say, the speed measured on going one direction as opposed to the speed you'd really like to have, which is vertical, they become appreciably different, and therefore. So for those two reasons, anisotropy and long offset corrections, the NMO equation that everybody should know by heart, doesn't apply. It doesn't work. So if you have offsets that are 3 times the depth, to be sure, when you stack these, when you take the best equation you can find, what you'll get is a final set of data looks like this. And this hockey stick look is because you've gone too far out with offset to use that equation. Some comments about semblance. This is from Eichel and Amundsen. It is a cross correlation with a different normalization discussed in Eichel and Amundsen. Terry Tanner and his friend Taylor. Terry Tanner recently died, but he was a massive applied mathematician in our business. He was the guy that invented the velocity spectrum, just to name one thing with Terry Tanner. So the whole velocity spectrum has his name as a patent when he worked beside John Delta. Semblance is just the particular type of cross correlation with different normalization used in the velocity spectrum, which an early version by Tanner, probably, most likely Tanner, or something that looked like this. You know it in Promax like this. And so this is nothing you haven't seen before. I do, that's a couple things I want to get to the Dix equation here, but before I get there, for the most part, root mean square velocity as a function of t0 time will be a constantly increasing thing. But if you can define a model like this, having this kind of a velocity inversion, or a model like this going from 5 to 2 back to 3.5, if your velocities can change that much, and these are in kilometers per second, then you in fact can take the root mean square velocity and turn it around. So just as soon as I say root mean square velocity always increases with time, pick to pick to pick to pick, there are situations that I can model that are plausibly geologically, and you might encounter. So it's not a hard and fast rule, it's a rule of thumb. Use that. And again, some of these look like something you've done in the laboratory. But I want to mention that in Promax, the interval velocity function is one of the options. It says you want to look at the interval velocity function as one of the items in that graphical user interface called the velocity spectrum. And this came from Hewitt-Dix in 1954. In fact, this is from Bob Sheriff's book, and the equation, I'm sorry to say, is not right. So let me just draw a picture here, and I wanted to give credit to Hewitt-Dix, and to say also that I've never seen before an error in Bob Sheriff's book, but this is an effect. If this is t0 time going this way and root mean square velocity going this way on a spectrum, if you have a pick here and a pick here, okay, each of these picks then has a root mean square velocity, which is this axis up here, and it also has a time, a t0 time. So they each have a root mean square velocity and a t0 time. If you want to know the interval velocity between these two picks, this equation does it. Its velocity interval squared is equal to, first off, the easy part. The denominator is simply this time here minus this time here. No surprise. The numerator is this point RMS velocity squared multiplied by its time to the first power minus this RMS velocity squared multiplied by its time to the first power. And if you look at that, here's time over here, here's time, velocity, velocity is equal to velocity across there, it's squared. So, this is a very handy equation. It was formulated by Hewitt-Dix about 10 years before you had even the common midpoint method being used today. But this is from Fred Hilton, and it lets us do some neat things. Let's go back to our first or second slide of the day, where we had not time, but time squared, and not distance, but distance squared. So that's a t squared x squared plot. And before we had points A and B on that first reflection, and we had then an intercept time for that reflection event, right? And we said we could get t0 squared, and the slope of this gave us 1 over VRMS squared for this shallow reflection. If that's the case, then we can get another reflection. Maybe this time we take a pick here and a pick here and maybe a pick there, 3 picks. A little bit better definition of the line. You get a second t0 time for a deeper event, and 1 over the slope of that straight line is the root mean square velocity of that reflection. Now, where are you getting this? You're getting it from a picture of a field file or a common midpoint gather. You got the reflection looking at it. If you can pick a time and a distance, you can do a time squared and a distance squared. Third, deeper reflection. Let's say we pick this time. Let's say we have 4 picks on this. Even a better picture of the straight line. There's this t0 time squared. 1 over the slope of that is the root mean square velocity squared. Squared. If that's the case, you then have a velocity function, because at 0 time, the velocity appropriate to that is the direct velocity from your field file, right? This next pick is the first t0 time and a VRMS, another t0 time and a VRMS, and another, and now you have 4 picks, and you can compute 3 interval velocities from here to here, from here to here, and lastly from the second to the last reflection event. So you not only have the ability to create a velocity between the two, you can make a velocity function and begin to pick interval velocities, 4 picks, and therefore 3 interval velocities. Guess what? If you know interval velocity right here, and you take the time difference between any of these 2 picks, say these two, and accommodate the fact that they're two-way times with this 2 number out here, now I can measure the interval thickness between those 2 reflections. Piece of cake. All I've got in front of me is a piece of data that came right off of your field monitor at the end of the day of a quick and dirty field file. Yes, sir?
What is the highlighted T0 for that interval thickness that you're referring to?
Let's see. Okay, I got a Z on the left. That's the thickness, Z, and I've got this is time. This is T0 number 1 and T0 number 2. Say these 2 here, this one here, and this one here, say, and you're going to then get the interval thickness between these last 2 reflection events, right? Because you know the interval velocity between the 2. It's a two-way time, and the rest of it is distance time difference. Distance equals rate times time due to this. Hey, if you know that, you can get average velocity. Not root mean square velocity, but average velocity. Because now all you got to do is sum up the Z here, and the Z here, and the Z here, there's 3 of them, and divide by the total time down to the last of the 3 reflections, and now you get average velocity, which will be different from root mean square velocity at that point, because they have a different formulation, and it's not quite the same. So what do you start with? You start with a piece of data on your desk. It's a common midpoint gather. Maybe it's a field file. It's got nice reflection of that. Somebody says, hey, give me a velocity function for that. Hey, give me a rough idea of how deep that is. What's the average velocity down to the deepest reflection? No computer inside, just your calculator. There you go. That's how you did it. Today you push the button. It's really pretty good. Here's the cautionary. You'll notice here it says, let's keep it close to home with your X's, right? You don't want to get too far out. X equal to Z, cool. X being twice as big as Z, not cool. And what will happen is, you'll try to put these on a chart, and what you'll get is think, and then kind of do a little thing. And it starts drawing something like that, right? But if X equals to Z, you get a pretty good straight line and a pretty good intercept. T squared X squared plot. Okay. Let me just close out by talking about multiples. They've been around as long as cockroaches. They're hard to get rid of. There's some clever ways using things called radon transforms that have a different formulation. The particular radon transform kernel is designed to do things for you there like Fourier does to give you isolation of frequencies you don't want. And then there's other techniques, but multiples can be very problematic. For one thing is, when you look at the final section, you're not sure if that's a real event that you just didn't know about, maybe a converted wave, maybe a structure you didn't think you had, or is it some sort of interbed multiple? You don't know. It's hard to tell. It's hard to tell. So a lot of times with multiples, it's very difficult to formulate what it should look like. Now, in a situation like landmark, back to landmark here. In this case, you had on this velocity spectrum, what you're going to have is a constant repetition showing up nice and big, because that is that energy trapped between the free surface and that hard bottom that's covered up the reef. And so this will stack like that. And in a real picture form, here's a good example of a multiple here that shows up here. And you'll notice it's not quite 2 to 1 because it's probably a peg leg. It probably has an irregular leg to it. So it won't necessarily come out 2 to 1. But whenever you have a velocity function that does this, it looks like it's trending like this, and all of a sudden there's something over here. It's not good. Don't be suckered into it because it's a nice big bullseye. Now when we get into dip move out, as a processing step and as a discussion point later, you'll see that it used to be when I was processing data for a living or in a research environment, a lot of times we would be dealing in structurally complex areas. And a lot of times we'd be in the foothills, say Alberta, and you would have flat layers and you would have the Cuesta initial structures in the same piece of world. And so what happened is you could either image the flat event or the steep dip event, but not both at the same time, because they would show up ugly on a section. And then along came the magic of dip move out, and we'll talk about that later as a processing step. Today that's been incorporated in pre-stack depth migration, sort of replaced dip move out. But I think dip move out is still important to look at as, and I think you're going to do it in lab. I don't know whether she's going to do it or not, but I'll wait and see. Okay, for the most part, if you're picking the velocity spectra, stay on the far side. Don't go inside. The only exception I would make to that is if you're in structurally complex areas that have flat and steep, sometimes the far side can be a problem all by itself. And that'll reveal itself when we talk about dip move out and the before and after on that. And I think I'm out of slides. Yes, there's a seminar forum with that too, so that's good. Okay, so let me hand this out. Questions on today's? Again, I recommend looking at nuggets. You'll get a tip. Yes.
For the decon
said most cases we don't know what the wavelength is. What are the cases when we do know the wavelength?
Hey, good question. You know, the wavelength, people try to find the wavelength a number of ways. They will sometimes hang a very clever hydrophone back of the ship, well short of the first trace on the streamer, and between the two air gun arrays, and try to measure 50 air gun pulses from a distance and sum them together. That'll work sometimes, but a lot of times if you're operating in shallow water, you'll get a ghost from the bottom, and you'll get the ghost from the top no matter what, because you put the hydrophone down in the water and the air gun is down below the free surface. There's a very, very quick ghost that you got to get rid of. It turns out in practice it's a pill. You think, oh, it's recorded. It's just a pill. It's hard to see it. They've done a lot of work with that. So wouldn't it be nice to have a good picture of the outgoing waveform, the wavelength, before it became non-stationary, but nevertheless, at least a picture of it, and you do deterministic spike and decon. Another times I've seen people just take the first trace and constantly try to separate the water bottom reflection from the first trace and snip that out and then look at it and sum it and do all that. And it works pretty well. It actually can work pretty well. And people who want to make a living at this will compare statistical decon with trying to make an estimate of the first trace and look at the two together. Say, yeah, I did well, I didn't do so well. You know, it's not easy. Otherwise, it's kind of like fiber size. Fiber size, you have a pilot sweep mathematically defined that you push into the ground. So you say, I'm going to correlate. What do you correlate with? Oh, I'll correlate with the pilot sweep. Well, maybe not. Maybe you put a geophone over here that measures not the pilot sweep, but what the ground actually took. Is that a better use? Is that a better gadget for the correlation process? It gets complicated in a hurry. What is the reaction mass doing with the ground? You know, for me to talk about it in 10,000 feet and get down to the nitty-gritty is two different things. But the neat thing is, if you're really interested in that, if you Google variations on fiber size correlation wavelengths, you'll get a dozen papers to look at that will show you the history of that in the literature, and you'll see names like Gary Cruz, who he's forgotten more about fiber size than I ever knew. I worked for the company that invented the term. Cruz has spent his life learning about fiber size and how to do it better. He works for spatial energy these days. He's an expert now. So if you just Google Gary Cruz fiber size, you'll get the best papers to read. So it's a very very big business, very complicated business. So pretty much it means everything I say is a white lie. I'll make generalizations knowing full well that in the specific, well, it's not quite right. It's like saying, here's the equation used for normal move out. Well, it'll get you halfway there. Okay. Do you have any questions about the exam? It's due in a week. Would you like one, sir?
Okay.
I'm trying to make the final exam smaller. People have complained, the final exam is too big. Okay.
We will be giving our assignments before starting final or some of your comments.
Yeah, the question again is,
are you going to get our assignments before starting final?
I'll check with it. I don't know if you can do that.
Because
I leave Duce kind of in charge of that. Oh, I did. Yeah, she's, 10% of your grade comes from your lab stuff.
Yes.
The main purpose of that is to keep your nose down to where you stay up with it so you don't get overwhelmed with, but 10% of your grade is to, be, and, you know, and everybody collaborates. The whole purpose of that is to stay with it.
And if we can get our assignments before starting the project, final project, we would know if we are doing well or not.
Whether she has graded them or not, yes. See good. I leave her independent of that and let her, I give her free reign because I grade her too. I mean, there's such thing as best TA in the department, and my people have won it 3 times.
So you're not
In the 12 years I've taught this, I've had 3 people that walk away with some money at graduation for best TA. I let her either hang herself or do really well. If I ran close on her, then it would be my work, not her work. Does that make sense? She's good. She's good. I like her. She's fearless. Charged with business. Other questions? So give me an email if you have any questions about this. Keep the pot pretty straight up, and see you later.